Hello, everyone, and welcome back. In the previous lecture, we introduced sequences, and critical to our discussion today is the definition of a Koshi sequence. Now, remember, a Koshi sequence is a sequence for which all of the elements are starting to cluster together. Remember, we have a precise definition for this, but that's loosely what's happening. Similarly, we have a definition of a convergence sequence, which tells us all the elements are getting close to a single value. We saw that convergence sequences are themselves Cauchy sequences. And what we're going to see today is in the real numbers, Cauchy sequences are also convergent. Now, what we are going to do is we are going to build on the discussion from the very first lecture, where I introduced different sets of numbers, and I purposely skirted introducing the real numbers. Today, what we're going to do is introduce the real numbers in the proper way that they should be considered. And the way that we're going to do this is similar to how we say introduce the integers as being sort of adding or including subtraction for the natural numbers. And for the rationals, what we did is we included division for the integers. And what we'll see today is that we're going to take sequences of rational numbers and include their limits in order to get the real numbers. So let's start off by proving that there is at least one element that is not in the rational numbers that is a real number. So let's put this as a little theorem. So this is that the square root of 2 does not belong to the rational numbers. Okay, so that is, there is at least one single number out there. There are many more than that, and we'll get into this more, but there is at least one single number that is not a rational number. So how are we going to prove this? Well, let's assume the contrary. So let's suppose the square root of 2 is a rational number. That is, so then there exists P and Q in Z, so two integers, such that the square root of 2 equals to P over Q. And we assume, or we can assume, P and Q have no common factors. Now, this is a very critical point of this proof. And this is an easy thing to have, right? Because we are just going to reduce the fraction so that it is in its lowest possible form. So again, 1 over 4, for example, is the same as 2 over 8. What we can do is we can knock off the common factor of 2 on top and bottom and get it in its most reduced form, 1 over 4. So we're going to assume that this thing is already in reduced form so that P and Q have no common factors. So then squaring both sides gives 2 is equal to P squared over Q squared, which gives us similarly that P squared is equal to 2Q squared. Now, 2 is an even number. P squared is a multiple of 2, making it an even number. So this tells us that P squared is even. And it's a very easy thing to show. So I recommend maybe pausing the video and trying this out, showing that if your square is even, then this tells you that P itself is even. But if P is even, it's a multiple of 2. This implies that P is divisible by 4, right? So this thing is divisible by 4, but then this tells us that Q squared is divisible by 2, aka it's even. Now this just comes from the fact that we have, if you look at this equation right here, P squared is divisible by 4. Only one factor of 2 is being pulled out of this. There is another factor of 2 that can be pulled out of p squared or out of q squared. But again, now we have a square that's even. This tells us that q is even as well. But here's the issue, right? Now we know p and q are both even. So this tells us p and q have a common factor of 2, which is a contradiction, right? Because we assumed that we got rid of all of these common factors. So therefore, the square root of 2 is not a rational number. We cannot write it as a quotient of integers. Now, why is this important? Well, this shows us that there is at least one number that is not in the rationals, right? So there's a number that sort of quote unquote exists that is not an element of the rationals. So the question is, how do we sort of construct this? What is it that this thing looks like? And how do we understand that such a number even actually exists, right? So I kind of just wrote it as the square root of 2. What actually is it? Well, what we could do is we could define a sequence. So what we could do is we could say define x1 is equal to 1, and x2 is equal to 1.4, and x3 is equal to 1.41, and x4 is equal to 1.414, and so on and so forth. And now, what you're thinking to yourself is, Jason, all you're doing is sort of writing out the decimal expansion. But that would require you to know what the square root of 2 is. No, that's not exactly what I'm doing. So we select xn to be the smallest, or sorry, the largest exactly n digit, so n digit number such that xn squared is less than 2, right? So for example, for x1, the smallest one-digit number that is going to be, its square is going to be less than 2, well, that'll be 1. And then for x2, I get 2 digits here, so I use 1.4. You can check if you do 1.5, that will, if you square that, it'll be bigger than 2. So 1.4, the square of that is still smaller than 2. Similarly, for x3, 1.41, if you use 1.42, you are larger than 2 when you square, and so this would not be a valid approximation. So although it looks like I'm just writing out the decimal approximation, I have a very specific rule that I'm following to build these things. Now, what we can see, we find xn is a Cauchy sequence. Now, why is it that we can see this? Well, if we go back for a moment, you can see that the first n digits of these things are going to agree, right? x1 and x2, they agree for the nth, or for the first digit. x2 and x3 agree for the first 2 digits. x3 and x4 agree for the first 3 digits, and so on and so forth. So that means that if n and m are greater than or equal to some capital N, we have the distance, or the absolute value of the difference between xm and xn. So m decimal points for xm, n decimals for xn. This is less than or equal to 1 over 10 to the n minus 1. Or sorry, less than that. And this is, again, just quantifying that decimal property, that you agree up to the first at least capital N decimals of your expansion here. And so this tells you that for n large enough, you can make this thing small. And this is telling you that your elements of your sequence are getting close together. Now, remember from last lecture, we said that convergent sequences are Cauchy, but we never proved that Cauchy sequences are convergent. And what we can see here, based on my first result, is that I have a sequence of rational numbers. And if we think that this thing converges to the square root of 2, then we can see that it converges to something that is not in the rationals. That is why we cannot say that Cauchy sequences are convergent sequences, because it might be converging outside of the set that you're working in. And this leads to the natural construction of the real numbers. So we had the Archimedean ordered field axioms that we assume. If we append one more axiom, then we whittle ourselves down from both the rational numbers and the real numbers to just the real numbers. And this is what's called the completeness axiom. Of the real numbers. So what this says is that every Cauchy sequence of real numbers has a limit in the set R of real numbers. Okay, so what does the completeness axiom do? It uniquely constructs the real numbers. And so again, think of the natural numbers. You put subtraction on that set, you get the integers. You put division on the integers, you get the rationals. Then what you do is you take the rationals and you say that all of the Cauchy sequences converge, you get the reals. This is the construction of the real numbers. And so this gives us the definition. The set R of real numbers this is an Archimedean ordered field satisfying the completeness axiom. And you can see now that when we had two Archimedean ordered fields, the rationals and the reals, this whittles it down because the rationals, the Cauchy sequences, do not converge to elements of the rationals, right? I just constructed a Cauchy sequence that does not converge, or it converges to the square root of 2, which is not a rational number. Okay, so what we're going to do now is we're going to use this axiom to prove the existence of upper and lower bounds on sets, and in particular, least upper bounds and greatest lower bounds. So again, let's start with some definitions here. So we say a number M is called an upper bound for a subset of the real numbers. So A, we'll call it in the real numbers, if and only if for all A and A, remember the upside down A means for all or for every, we have A is less than or equal to M. And we can say similarly, a number, so we like to use little m for lower bounds. So this little m is called a lower bound. So we put it in red so that we can emphasize this the definition. So it's called a lower bound if and only if for all A and A, we have A is greater than or equal to little m. Okay, then let's go a little further. We say a set A is called bounded provided it has both an upper bound and a lower bound. So if you can find an upper and lower bound on that set, then you have a bounded set. Now let's push this even further, right? I've got a little bit more that I want to add to this definition. So we say a least upper bound so a least upper bound for a set A of the real numbers is an upper bound L for A such that no number, let's call it L prime, which is smaller than L, is an upper bound of A. Right, so it's the smallest upper bound that you could possibly find. And we say a least upper bound is denoted by LUB of A. Okay, so there's also a notion of this that comes with the lower bound. It's called the greatest lower bound. We'll get there in a moment, but I don't want to overwhelm you with definitions to start with. Right, so an upper bound just means that there is a number that's bigger than everything in your set. A lower bound says there's also a number that's smaller than every element of your set. You are bounded if there exists upper and lower bounds. And you call a least upper bound the smallest possible upper bound you can make. Now, here's the interesting theorem. This is where the completeness axiom is going to come in. But this theorem tells us that if a non-empty set, so it has to have something in it, set S has an upper bound, then S has a least upper bound. So again, think about this in terms of everyone's ages in the room, right? So there is, I'm going to venture a guess that 1,000 years old is an upper bound on everyone's ages. That is that's a very loose guess, right? I don't think anyone has ever lived to be 1,000 years old, so it's pretty safe to say that that's an upper bound. But what this theorem says is that if you can find any upper bound, no matter how terrible it is, you can also find a least upper bound. So say everybody in the room, the oldest person in the room is 81, then 81 is your least upper bound. Even though 100 would do the trick or 99 would do the trick, 81 is the smallest upper bound that you're going to be able to find there. Okay, so let's take a look at the proof. And the method of proof here is really fun. It's really cool, and it's one that you're going to see a few times over the course of these lectures. So since S does not equal to the empty set, so this might be new notation for you, then there exists some S in S, right? So I can always find something in there, right? The room at least has one person in it whose age I can measure. Now select any number, we're going to call it A1, which is less than little s. Right, so I just ask one random person in the room. I say, how old are you? I say 31. Okay, so I pick a number smaller than that. I pick 2. Doesn't matter what it is, but this number exists. So any number A1, so that A1 is too small to be an upper bound on capital S. So we're going to use a method of proof called interval halving. So here's the basic idea. Let's also let B1 be an upper bound on S. Remember, this exists. The theorem, if S is a non-empty set, has an upper bound. So we know that this exists. We have to have some B1. Here's what we'll do. We'll cut the interval A1 to B1 in half. So the midpoint between A1 and B1 is A1 plus B1 over 2. And here's what we're going to do. Case 1, if the midpoint, if this thing is an upper bound on S, then we found a new upper bound that's smaller than B1. So we're going to call this B2. So let B2 equal to A1 plus B1 over 2. And let's use A2 to be the old A1. In the other case, but if A1 plus B1 over 2 is not an upper bound on S, then let B2 equal to B1 and let A2 equal to the new point here, or the midpoint. So what this does is this cuts the interval in half, right? So you have A1 to B1, and you look at the midpoint and you choose the interval that S lies inside of. So I'm going to do this pictorially for a moment. Let's imagine we have a line here, and this is going to be A1 and B1. And let's pick a value for S. Let's just say S lies right here. And what you can see is my midpoint should be approximately around here. So then the next step down is going to choose that half interval that has B2 as its endpoint, which is the old midpoint. So this gives me B2, this gives me A1, and now you can see that you have S lying inside of this thing. And the next step, you are going to find the midpoint of this interval. So let's say it's right here. This is going to be A2 plus B2 over 2. Sorry, this left endpoint, let's be consistent. This would be A2 now. Then you choose the half interval here that S belongs to, and you repeat the process again. So now you have another half interval. So you have B3. So if you just keep using the same repetition between case 1 and case 2 above, just increasing the index, and you have A3. Now you can see that you have S lying right here. And let's just draw one more example here. So again, I'm going to take the half interval here, A3 plus B3 over 2. You can see it lies in the left half. So you're going to choose that interval now. And what you get is A4 and B4. And this is getting a little tight, but you can see S is maybe over here. And I can divide that interval again. Sorry, this is getting a little cramped, but you can see that at every single step, you are having the interval and you are always inside of that original interval that you started with. So this will So repeating defines a sequence, sequence AN and another sequence BN such that AN is less than or equal to S for all n greater than or equal to 1. This is by design. And Bn is an upper bound on S for all n greater than or equal to 1. So the A's cannot be an upper bound because they lie below the element S, but the B's are an upper bound for the entire set S, okay? Now, here's the important piece. This is actually a Koshi sequence. So what we find, so these are Koshi sequences. So let's see this. Well, why is this the case? Well, if you look at the difference between successive points for any capital N, this is the length of the original interval. So that's the distance from B1 to A1. And then you've halved it n minus 1 times, right? So again, just take a look at my little picture here. The distance from B2 to A2, that's half of the distance from B1 to A1. Similarly, the distance from B3 to A3 is a quarter of the distance from B1 to A1. And you can see that this goes to 0 as capital N goes to infinity, right? The top is fixed, it's not moving. And so to see that these things are Cauchy, we can say thus, if epsilon is greater than 0, there exists a capital N, right? So based on what I just showed above, such that B capital N minus A capital N is less than epsilon. And this also says that if you look beyond that capital N, just by design, again, take a look at the picture that we just drew. If we have 2 points beyond this capital N, this implies that AN minus AM is less than epsilon, and BN minus BM is less than epsilon, since BN, BM, AN, AM are all in the interval A capital N to B capital N. And this just comes from the fact that you are always using points from the previous interval to get the next interval, right? So you're just sort of layering down. So AN and BN are Cauchy. And so from the completeness axiom, these are real numbers. Remember, this S is a subset of the real numbers. And so therefore, they are going to converge. So from the completeness axiom, there exists A and B, real numbers, such that AN converges to A and BN converges to B, right? And this just comes from the fact that we identified a Cauchy sequence of real numbers. Actually, we identified 2, AN and BN. And the completeness axiom says that all Cauchy sequences in the real numbers have to have a limit. Okay. Now, we can also find, so with a little bit of argument that I'm going to omit, we also find that A and B, they belong to A capital N and B capital N. So this might take a little bit of extra argument, but I urge you to try this all on your own. And this is for all capital N greater than or equal to 1. And so thus, the distance between these 2 points in absolute value is less than epsilon, because A capital N and B capital N, the distance, the width of that interval can be made as small as possible. And this is true for all epsilon greater than 0. Now, what this means is that I pick something that is not a negative number, so it's 0 or bigger, that is smaller than every possible positive number. So therefore, the only possibility is if this is 0. So this gives that A minus B is equal to 0, which tells me that A is equal to B. That's interesting, right? Because that tells me that A and B are Cauchy sequences converging to the same thing now. So we claim that the number, right now it's a single number, I'll call it L for limit, which is equal to A and equal to B, is a least upper bound for S. Okay, so first note that AN is less than or equal to L, which is less than or equal to BN for all N greater than or equal to 1. You can argue this in a really, really nice way, but this is important, right? Because your limit, A is approaching it from below and B is approaching it from above. You're sort of sandwiching in on that limit L. Okay, so first, we can observe that if S is an element of S, then S is less than or equal to L. Why? Well, if S is larger than L, if S is larger than L, then we can set epsilon equal to S minus L over 2. And since Bn is convergent, then there exists a capital N such that Bn minus L is less than epsilon. That's just using the fact that this is a convergent sequence, which we can open this up. We get minus epsilon is less than Bn minus L, which is less than epsilon, which tells us that minus epsilon plus L is less than Bn, which is less than epsilon plus L, which, if you'll bear with me, I'm going to put a division or a divider line here so that I can continue the manipulations on the same page so that you can see everything all at once. But let's use the definition of epsilon. This becomes negative S minus L over 2 plus L is less than Bn, which is less than S minus L over 2 plus L. And so in this case, I get 3L over 2 minus S over 2, sorry, is less than Bn, which is less than S plus L over 2. Now you might be wondering what the issue with this is, but let me circle something for you and point out where things are going to go wrong. This term right here. So what do we know about this term? Well, we know that S is less than or equal to L. And so if I can pull that term onto the next page here, I get Bn is less than S plus L over 2, which is less than or equal to L plus L over 2, which is equal to L. Okay, so what's the big deal? What's the problem with this? Well, let's take a look. We assumed from my note here that L is less than or equal to Bn. We actually didn't assume it, we know this. And so this is impossible. So this is impossible since L is less than or equal to Bn. So thus S is less than or equal to L for all S in L, which implies that that L is an upper bound on S. Okay, so that one took a little bit of work, but we got it. Now we want to claim, so finally, we want to show that L is a least upper bound. So we claim L is a least upper bound on S. Well, if we suppose there exists some L prime less than L such that L prime is an upper bound on S. Well, again, we can follow similarly as above. We can use the fact that AN is converging to L to find ANs which are below every single S or below at least some element of S. So we can find ANs above L prime, which implies some of the ANs are upper bounds on S. But this is impossible. So in this case, let me draw you a picture for what it is that's happening. So L is a least upper bound. Okay, let me draw a picture so that everybody knows what's going on here. So here is my value of L at the very right of my line. And what I know is that I have ANs, so say A1, A2, A3, A4, A5, A6, right? And we are packing in and approaching, right? So AN is approaching L as N goes to infinity here. So if you tried to take another, say L prime, well, you're going to get all of these ANs above you. And since L prime is an upper bound, then all of those ANs are also upper bounds, right? If I say there's no one in the room older than 80, well, then there's also no one in the room older than 90. And so this is obviously not true. Again, just coming from my note here, because my note says that AN is not an upper bound. It is smaller than every single or smaller than at least one S in the set because, or by construction, if you look at my picture here of how we defined the A sequence. And so this shows us that we have, in fact, a least upper bound on our set. Okay, so that was a hard proof, right? That was a lot of work. It took a lot of steps, but we got it. What I want to do, first of all, is immediately address a corollary here. So corollary, this is an immediate consequence of this. And it says that if S is a non-empty set of real numbers that has a lower bound, then S has a greatest lower bound. Now, we did not define a greatest lower bound, right? My definition stopped at least upper bound. So it is worth taking a second to think about what a greatest lower bound actually is. And a greatest lower bound is the biggest lower bound that you can get on a set. So the same idea as the least upper bound. It says the greatest lower bound, if you try to find another lower bound, it won't work, right? There's nothing that's going to be able to do that. Now, this proof is done in almost exactly the same way. I'm going to leave it as an exercise, but it's an interval halving technique again. And I want to put a little note here. So we denote the greatest lower bound by GLB of S, right? So just like the least upper bound is LUB of S, well, the greatest lower bound is GLB. Now, there's something to address here, right? These two results tell you that if you can find lower bounds, then you can find greatest lower bounds. If you can find an upper bound, you can find the least upper bound. But what if you're unbounded, right? Think about the counting numbers, the natural numbers. There is no upper bound on the counting numbers, right? That's what the Archimedean property assumes. So what happens here? How do you denote the least upper bound? Well, we have slightly different notation for this, and this comes in the form of the following definition. We're going to say let S be any non-empty subset of R, and we're going to define what we'll call the supremum. So the supremum of S, and we're going to denote it sup of S to be the least upper bound of S if S is bounded above. So if it has an upper bound. And define sup of S equal to infinity if S has no upper bound. Right? So the previous theorem told us that if you have an upper bound, then you have to have a least upper bound. So whatever, if you have an upper bound, you're bounded above, then your supremum will return that least upper bound. But if it is not bounded above, the supremum just says infinite, right? It's sort of like a does not compute type thing. Well, we have the same idea for the greatest lower bound. So similarly, define the infimum. So let's put this in red. Infimum of S, and denoted inf of S, and let that be, so to be the greatest lower bound of S if S is bounded below, right? So that corollary tells us that if you have a lower bound, you have a greatest lower bound. And we will define inf of S equal to minus infinity if S has no lower bound. So a lot of definitions today, right? It's taking a little bit of work, but this is important. This is certainly important for us. We need to have the proper definition so we know that we're all talking about the same thing at the same time here. So you can think of these things as sort of functions. And let's take a look at some examples to close out this lecture. So let's say let S equal to the set of x's such that x is between 0 and 1 exclusively, right? So this is the open interval from 0 to 1. Then I'm going to claim that the supremum of S is equal to 1, so it's not in the set, and the infimum of S is equal to 0. Let's do a little proof here. Let's start with the supremum. The infimum is handled in exactly the same way. So first of all, clearly, 1 is an upper bound on S, right? So it's bounded above, right? I could have chosen 2 or 3 or 8 or anything like that. This has a upper bound, and by the previous theorem, this tells us that there is a least upper bound. So, but if m is less than 1, then there exists some x in S that is bigger than m. And so thus, m cannot be an upper bound. Of S. So therefore, the least upper bound of S is equal to 1. And so the sup of S is also equal to 1. And I'm just going to put a note here. The argument for inf of S equal to 0 is nearly identical. So I want you to try and work that one out yourself. And the last example that we'll do is the supremum and the infimum of the natural numbers. So first of all, the supremum of the natural numbers, I had already said this. This thing is unbounded. There is no upper bound on the natural numbers. Again, that is just the Archimedean property. And so therefore, this supremum is equal to infinity. Also, the natural numbers are bounded below, right? There are no negative numbers in the natural, so therefore any negative number will act as an infimum. Similarly, 0 acts as an infimum, 1/2, 3/8, all of these numbers all the way up to 1. 1 is itself a minimum of this set. And of course, if you choose a number that's larger than 1, then you are no longer a lower bound because 1 is itself a natural number. Remember, we're assuming that the natural numbers start at 1, as we pointed out in the first video in this series. And so the infimum here is equal to 1. Okay, so what we've seen today is the way that we can sort of define or construct the real numbers from the rational numbers. And this comes from the idea of the Koshi sequences. So we added another axiom to our Archimedean ordered field in order to get the real numbers, and that is the completeness axiom. Then what we saw is how we can put the completeness axiom into use. We saw this with the proof of upper bound means that you have a least upper bound, sorry. And we did this through an interval halving procedure, which eventually resulted in a Cauchy sequence, which we knew was going to converge due to the completeness axiom. And then we found that its limit point is actually the least upper bound. That proof it was complicated, it was long, it was slightly difficult, but nonetheless, we got through it and we got to see how to use the completeness axiom.